This is my second example from today's class on February 25th. And again, I'm working with the same system as before. This came from a damped harmonic oscillator from a second order equation, same system as in the previous example. Same two known solutions. And starting next class in section 3.2 and again in section 3.4, we're going to address where do we find these solutions? How do we actually have techniques? We have one technique for finding them, but we're going to discover some others using eigenvalues and eigenvectors. But nevertheless, I have a solution known as y1 and a solution known as y2. And they correspond, as I showed last time, y1 corresponds to the segment that starts right here and moves towards the origin, and y2 starts at 1 minus 1 and moves towards the origin. But suppose I want a solution. I want to know, well, what's the solution that goes through the point 2, 1? So roughly 2, 1 would be 2 in the y direction and 1 in the v direction. Our solution needs to pass through this initial value. And I can see just by following the direction field that it's going to, if I can graph it, it's going to look something like this. Okay, and if I could use Runge-Kutta or one of the numerical techniques, I would see it would start at the red dot and follow in towards the origin, again never reaching the origin, but that's the curve we're after. Our theorem tells us that if we have two solutions that are linearly independent, then we can find the solution that goes through any initial point anywhere in this plane. So I've chosen this point as an example. Well, first is the test for linear independence. And so we have to check for linear independence. And for that, we look at the two initial values of our two known solutions. We look at what y1 is at time 0. Plugging in 0, I get a 1 minus 2. And what is y2 at time 0? Plugging in 0, I get a 1 minus 1. I asked the question for linear independence, are these two vectors linear constant multiples of one another? Can I multiply this by a constant to get this? And the answer is no. A better test or another test would be to look at the determinant. And so I look at the determinant made up of columns. So I choose this to be my first column, 1 minus 2. And I choose the second one to be the second column. And the determinant, if the determinant is 0, they're not independent. If the determinant is non-zero, they are. This determinant ends up being a negative 1 plus a 2 is 1. And so that's not 0. So we have linear independence. That's good. Check. The general solution theorem says that what the solution is going to look like, now that I know I have linearly independent, two linearly independent solutions, they're going to look like, the solution is going to look like k1 times y1 plus k2 times y2 for an appropriate choice of k1 and k2. Well, I don't know if I have enough room to do it on this page, but we'll try. So we know from the linearity principle that that this is the sum of these two functions will solve the system. The linearity principle says hey, if you have two solutions, and if y1 is a solution, a constant times y1 is still going to be a solution. And if y2 is a solution, a constant times y2 will be a solution. And a sum of two solutions are solutions. All that comes from the linearity principle. So I know this expression is a solution of star, of this linear system. But we have to find the k1 and k2. But now that I know I've got linearly independent vectors, that won't be a problem. And so what we set up next is we look at the initial condition and we say, well, this solution that we're building at time 0 better equal to 2, 1. That's what it's supposed to equal. But if this is its form, then at time 0, that's going to be a k1 times y1 at 0, which we know to be 1 minus 2, plus k2 times y2 at 0, which we know to be 1 minus 1. And this leads to a system that says k1 plus k2 will be a 2, and a minus 2k1 minus a k2 has to be a 1. So I'm just reading across. The k1 multiplies the 1, the k2 multiplies this 1. That sum has to equal a 2, and when k1 multiplies minus 2 and k2 multiplies minus 1, those two have to add up to be a 1. Two equations, two unknowns, easy for us. If I add these two together, the k2's will drop out, and I'll end up with a minus k1 is equal to a 3. So k1 is equal to minus 3. And it'll follow that k2, if k1 is a 3, k2 will end up being, if k1 is a minus 3, k2 will end up being a 5. I think that's right. Yes. And we'll check it for sure. Okay. So those are my values. I'm going to go to the next screen and just make sure everything is right. So let's just check that. Always good to check it. So is it true that that our solution function that looks like minus 3 y1 plus 5 y2 solves the initial value problem? Well, at time 0, I have minus 3 times, apologize, I have minus 3 times 1 minus 2, and I have a 5 times 1 minus 1. And does that take me to the point 2, 1? Well, a minus 3 plus a 5, that's sure enough a 2. And a 6 minus a 5, sure enough that's a 1. So yes, this expression, this function, sure enough, at time 0 is at the point 2, 1. It's at the point 2, 1. That's good. And I don't have to check any further. I know that that this solution, this function, satisfies the linear system known as star, because the linearity principle says since this is a solution of star and this is a solution of star, any sum of two solutions are solution of star. And so the one unique function, and if I wanted to write it out in more detail, I could say that y of t is minus 3e to the minus 2t plus 5e to the minus t. And 6e to the minus 2t minus 5e to the minus t. This would be our solution. This would be our x of t. And this would be our, I apologize, I keep using x's and y's instead of y's and v's. So this would be our y of t. This is how our position is behaving, and the bottom term is our velocity. And that's it. Thank you.